This is part 3 of example 3 of the Coulomb's law videos. What we're going to do in this question is to find the point charge location and magnitude given the E that we solved for in part B. So we know the magnitude of the electric field and we know the direction of the electric field. What we're going to do here is find a point charge somewhere on the z-axis and its magnitude that would give us that the same electric field magnitude and direction. We're going to do that with Coulomb's law. And just as a reminder, we're solving for Q and R. This is just a reminder from the previous video on what we actually solved. The main part of that question was getting this dE. So we solved for dQ, we solved for R, and we solved for A hat R. Just as a reminder, this is what we solved for in the previous question. We solved for dQ, we solved for R, and we solved for A hat R. And this is the expression that we got out of that. What I'm going to do with this now that will be helpful for this question is I'll draw out what this looks like. I know this sounds scary at first, but I'm not going to be super accurate with the diagram. It's just a sketch. That's all it is. It's just a sketch to help us out. You don't have to be perfect with the drawing. dE will go off in some direction this way. The reason being is that there is some rho component and a z component. I'll draw that in. Here you can see the rho component of dE. Here's the z component of dE. E was just found by taking the integral of dE. I made a mistake here. I've actually forgotten the vector signs over the top, so you could draw these in. I'll just draw a sketch over here. There's a vector sign here and a vector sign here. So those are vector signs. And we can go from dE to E just by doing integration. In terms of the diagram though, it's pretty much the same. I'm going to ignore any scaling going from dE to E. It's the directions that matter most at this point. Here's the full diagram. This is E drawn over here. As you can see, there's a rho component and a z component. You can see how similar it is to the dE diagram. It's the directions that matter most in this situation. I'm using the rho phi z convention as I have in the previous videos, and you can see here that we have 5 in the rho direction, 3 in the z direction, and I've mentioned in the previous videos why I gave phi a value of 0. Similarly, you can look at the point over here. This is the location of that point charge that we're interested in. You can see that there's the z prime notation over here because that's the source of the electric field. And I've just given its magnitude to be Q, just out of convention. Let's move along now and solve the rest of this question. This is part of my position vector, going from this point charge to this point of interest over here. So I have some component going in the z direction. There's a component in the rho direction. These two components together give us the vector going from this point charge all the way to the point of interest. As you can see here, all I've done is taken this three-dimensional diagram and drawn it in 2 dimensions to make things easier to see. I can do this because, well, everything's in the phi equals 0 plane. So really I can just write my vectors in terms of the rho and z components. The points are still the same and everything is drawn in the phi equals 0 plane. That's why this is possible. Both points are in the same plane. This point over here is 5, 3. As you can see, that's the same as 5, 0, 3 that I've drawn in this three-dimensional diagram. And this point over here, the point charge location is 0, z prime. Again, I'm using the prime notation because that's the source of the electric field. That's the same as this point over here in this three-dimensional diagram. What's cool about this is that now you can easily see that all this is just a line. And in 2 dimensions we had learned in the conventional y-x coordinate system, or xy, however you'd like to describe it, we learned that, well, to find the equation of the line it was just y equals mx plus b. In this case, however, we're not using y and x, we're using z and rho. So I'll call it z equals m rho plus b. And that's this line going from the point charge all the way to this point of interest. I've cleaned that up a bit in this slide over here. You can see that z is m rho plus b. And I've taken the rho direction, in this case, to be positive, going this way, so I don't have to worry about any negative signs in this expression. How I found the slope is quite simply just using my solution from part B. I found the magnitude going in the z direction, the magnitude going in the rho direction. Divide these two and you get 1.766 approximately as your slope. And now, because we have the slope and because we have a point on the line, we can easily find what this b, what this intercept is, this z-intercept. And the z-intercept is this location of the point charge. So once again, I know the slope, I'm looking for the z-intercept, and I have 3 on the z-axis, my rho equals 5, and I have the slope. So I can easily find what this z prime is, just by simple algebra. So I plug all these values over here, into this equation. Finally, that gives me a z prime of approximately negative 5.831. So I know that the charge is located at negative 5.831 on the z-axis. That makes a lot of sense intuitively if you think about what that negative half line looked like. It was a line just in that negative z-axis. So you'd expect a point charge to be somewhere along that same line to give you the same electric field at a given point. Now that I know where the charge is located, I can easily find what the magnitude of that charge is just by Coulomb's law. So, because I know that the z prime is actually negative 5.831, I can subtract 5, 3, and this point over here to give me the direction vector over here, going from this source to the point of interest. And once I have the vector, I can easily calculate the magnitude. I have r as 10.148 meters, and I found the magnitude of E from part B. So I have what E is, I know what r is, epsilon naught is just a constant. So I can easily find Q just by simple algebra once more, and I find that to be 81.185 nanocoulombs. That marks the end of this example. You can see that throughout this third example we have really useful applications of the simple things we learned with the infinite line of charge. So we can see that these building blocks are really crucial to solve complicated problems, and if you've understood the infinite line of charge, that gives you a key to a whole lot of problem solving that you can do. Thank you very much, and I'll see you in the next video.